Hi everyone, my name is Anas Manzoor and I am PhD candidate at University of Wyoming. First of all, I am thankful to the organizing committee for giving me opportunity to present my research work. Today I'm going to talk about point defect energies in concentrated alloys using machine learning methodology. Now to start with the introduction, concentrated solid solution alloys are a class of metallic alloys in which multiple principal elements are randomly placed on a crystal lattice, as you can see in this cartoonic figure. These alloys normally have FCC, BCC, and HCP crystal structures with distorted lattice. These alloys have shown good mechanical and radiation damage properties. As an example, in this plot, you can see that the vertical axis is the ductility and the horizontal axis is the tensile strength. And conventional alloys are lying on this red dotted line, which shows that there is a trade-off between these two properties, meaning when ductility is high, strength is low, and vice versa. Whereas concentrated alloys are lying in this red shaded region, which shows that they have a high strength and high ductility at the same time, which is a unique combination and never observed in other conventional alloys. Similarly, improved radiation damage properties are observed in these alloys. In this bottom plot, the vertical axis is the step height corresponds to swelling in the material caused by the irradiation environment. And some of the considered alloys are lying in this region, um, and they show that they have a significantly reduced swelling compared to nickel. Now, due to random arrangement of elements, the local chemical environment around every lattice site and point defect is different. As you can see in this cartoonic figure, both these vacancies have different nearest neighbors and different lattice distortion, which leads to wide distribution in the defect energies. As an example, I am showing the vacancy migration energies and vacancy formation energies in two iron nickel chromium based alloys. And in the case of migration energies, you can see that the range is between 0.81 and 1.8 ev. And similarly for the vacancy formation energy case in iron 17 nickel 10 chromium 20 alloy, the variation is quite high and energies are between 1.65 ev to around 2.3 ev. So apart from large variations in point effect energies which exist anyway, number of calculations also influences the distribution in the energies. So for example, in this bottom plot, the vertical axis is the vacancy formation energy and the horizontal axis is the number of calculations. Zhao et al. And Guan et al. Both performed calculations on this equiatomic alloy, and Zhao et al. Performed twice the number of calculations, and you can clearly see that the variation is also twice. So this shows that to capture the right distribution in the defect energies, large number of calculations are important. Uh, Now, atomistic methods such as density functional theory and interatomic potential used to calculate the defect energies. DFT calculations are reliable, but there's a major limitation that these calculations are very expensive. And in concentrated alloys, there's large number of compositions possible even within the same chemistry. For example, in this plot, this orange area shows the compositional phase space for the concentrated alloys, and you can see that there are large number of possible compositions can lie in this area. And as the number of elements increases in the base alloy, the number of compositions also increases exponentially. So the challenge compounds when one has to calculate the defect energies using DFT in large number of possible combinations. And there is a need to develop a strategy through which these expensive and large number of calculations can be bypassed. To deal with this computational problem, our idea is to make a database of binary alloys and then using machine learning framework predict the defect energies of higher order multi-elemental alloys. And this idea is shown in this schematic. With this strategy, once the database is built for binary alloys, then the defect energies of any concentrated alloy can be readily available without doing any calculations. Another advantage of this framework is um, the defect energies of those compositions can be predicted, which are unearthed or will develop in the future. Now, our main idea is to develop a framework for the DFT calculations, but we want to take the advantage of interatomic potential calculations, as these calculations are relatively cheaper and large number of calculations, thus a large number of data points easily gathered. So we have developed a machine learning framework for interpotential calculations, and our next step is to develop or test this framework on the DFT calculations. Um, so we have calculated defect energies, vacancy migration and formation energies in these FCC disordered alloys based on these five elements, which are nickel, iron, chromium, cobalt, and copper. We use lamps to perform these simulations, and Farkas-Caro EM potentials was used in these simulations. Lastly, a big supercell size containing 864 atoms um, used to perform these simulations, so that and in this case, we have calculated the defect energies for most of the sites. So now, as I mentioned earlier or discussed the idea to make a database of binary alloys and then use this database to train the model and predict the defect energies of ternary, quaternary, and quinary alloys. Here I'm showing the considered alloys we use for the training and testing of the machine learning model. And based on these five elements, 10 binary alloys are possible. And then once we train our model using these binary alloys, we are predicting 8 ternary, 5 quaternary, and 1 quinary alloys defect energies. Now, first, I want to talk about the predictions of migration energies using machine learning framework. Here, I am first talking about the descriptors we use for the migration energy model. And the descriptors are based on the local chemical environment around migrating atom and the vacancy. So in this figure, the empty circle is the migrating atom and the empty square is the vacancy. The migrating atom is jumping to the vacancy site, and these green and blue atoms are the first nearest neighbor atoms to the migrating atom and the vacancy. We categorized or divided these nearest neighbors into four different categories. Um, First category is CNN, common nearest neighbor atoms, middle nearest neighbor atoms, common back nearest neighbor atoms, and BNN back nearest neighbor atoms. So there are four common nearest neighbor atoms, two MNN, four CBNN, and one BNN atom. Now, this is the representation of our spreadsheet used for migration energy model. And we are using four types of descriptors. So first type of descriptor is the type of the migrating atom. So this atom can be a nickel or any other element. The second type of descriptor is the distance covered by the migrating atom to reach to the or jump to the vacancy site. And then we have the orientation of X element, which means orientation, for example, which element or atom is sitting on the PNN position. So similarly, for we are recording this information for all the nearest neighbors, which you can see in this extension. And lastly, the fourth type of descriptor is the distance between the migrating vacancy and their nearest neighbors. So for example, again, the distance between the migrating atom and the BNN atom and their extension, because we are reporting all the distances with their nearest neighbors. Now, the important point to note here is all these descriptors are based on the perfect supercell, so that when you want to predict the migration energy, you do not need to do any extra calculations. Now for the training of the model, we use sport vector regression algorithm, and holdout method is used where 20% data is used for the testing of the model. And lastly, two statistical tools, Pearson correlation coefficient, R, and root mean square error, RMSE, is used for the evaluation of the model to check the performance of the model. So now let's talk about the prediction results. Here in this slide, I'm showing the training and testing on the binary alloy compositions. So this plot is for nickel 50, iron 50 alloy. And the vertical axis is the machine learning predicted migration energies, and horizontal axis is the LAMS calculated migration energies. Orange data points are for the testing data set, and blue triangles are for the training data set. And you can see that the model performs well for the testing data set with high R 0.95 value, and RMS is quite low, 0.04 EV. Similarly, we tested our models on some other binary compositions also. The important point is in the iron copper case, you can see that the wide distribution in the migration energies, and model is able to predict or capture this wide distribution quite well. And you can see the RMSE and Pearson R value for testing data is quite high. So overall, our model works on the binary compositions. Now, the real test of our model is to, which is our main concept, to train on the binary compositions and predict on the ternary. So first, we tested our model on the nickel iron chromium alloy, and for nickel iron chromium alloy, the constituent binary systems are nickel iron, nickel chromium, iron chromium. So we use these three systems, which with the various compositions for training of the model, and then we are predicting migration energies for nickel iron chromium. Initially, we used a high number of data points. So for example, here the training data set includes 11,400 data points. We considered compositions at 5% interval, which means that we are, for example, for nickel iron, we are including nickel 5, iron 95, nickel 10, iron 90, and so on and so forth. And from each binary composition, we are using 200 data points. And you can see that for this equiatomic nickel iron chromium, the predictions are very accurate. R is 0.96 and RMSE is 0.05. Now, 11,400 calculations with DFT, it's not practical. So we systematically reduced the size of our training data set, and we came down to only 120 training data points, meaning from we are only considering um, the compositions at 20% interval and only 10 data points from each binary composition. And here also you can see that the predictions are very accurate with the high R, which is zero point 0.9, and RMSE is 0.07. Now, this is just one composition. We actually predicted the migration energies for 15 other compositions in nickel iron chromium. And this plot shows the ternary phase diagram, and we are showing the Pearson correlation coefficient values. And the important point again is only 120 data points are used for training of the model. And you can see that the R values are above 0.85 at least. Actually, they are close to zero point 0.9. And I do not have space for the RMSE, but we know that the RMSE values are also below zero point 0.1 EV. So the predictions are very accurate for the nickel iron chromium. Now, moving forward to other ternary alloys also. So we use the same strategy to train our model using the constituent binary alloys. Now, nickel iron chromium results you already saw in the previous slide. Now, this here I'm showing the nickel iron cobalt and nickel iron copper. Here also the predictions are quite good with the R value is greater than 0.85 and RMS is also below 0.1. Similarly, we tested our model on quaternary alloys. I'm just showing the two examples of equiatomic nickel iron chromium cobalt and equiatomic nickel iron cobalt copper. And here also you can see that actually the R values are greater than zero point 0.9 and RMSE is again smaller than 0.1 EV. Now the ultimate challenge is to predict the migration energies of quinary alloy from their constituent binary alloys. And this plot shows the equiatomic nickel iron chromium cobalt copper results. And you can see that the predictions are very accurate with the R 0.95 and RMSE 0.07. So overall, what was our hypothesis or our idea that we want to predict the migration energies from binary alloys for these ternary, quaternary, and quinary, which we are able to get. Now moving forward towards the predictions of vacancy formation energies using machine learning framework. Again, first I'll start with the descriptors we use for the formation energy model. Here in this case, the descriptors are based on first nearest neighbor environment and also on the second nearest neighbor environment. In this figure, the square, empty square is the vacancy, and then you have the first nearest neighbors in the top figure. Each first nearest neighbor classified into an orientation vector. So for example, For this green atom, I'm saying this O1 term, and O1 is orientation vector, which is 1, 0, -1. And 1 corresponds to A direction, 0 corresponds to B direction, and -1 corresponds to C direction. So just for the A direction, as you can see that the this atom is sitting above A00 plane compared to vacancy. So that's why positive one is given. And similarly goes for other directions also. And this we did for a second nearest neighbor also. In the case of second nearest neighbors, you just have six second nearest neighbors, and for each nearest neighbor, we are giving a vector. Now here also we use four types of descriptors. These four types of descriptors are slightly different from the migration energy model, because here we are also including the second nearest neighbor atoms also. So first type of descriptor is the type of the vacancy, like the atom you are removing to create a vacancy can be nickel or any other element. And then you have the distance between the vacancy and the atom sitting on the O1 direction. And so that's why you have 12 columns for these distances, because you have 12 nearest neighbors. And similarly, the orientation, meaning which atom or element is sitting on this O1 position. And same goes for all other nearest neighbors. And fourth type of descriptor is for the second nearest neighbors, we are including just the distances between the vacancy and the atom sitting on that orientation. Again, here also, these descriptors are based on perfect supercell, so that no extra calculations are required for the predictions of vacancy formation energy. Same strategy we used here also, support vector regression algorithm is used, and same statistical tools are used to evaluate the performance of the model. So here I am showing the prediction results. Um, we use the same strategy as we used in the migration energy case. Here I'm showing the results for ternary alloys, and these are the three ternary alloys, and you can see that nickel iron chromium predictions are very accurate with R.95 and RMS is 0.08. For nickel iron cobalt and nickel iron copper also, the predictions are quite reasonable with R is greater than zero point 0.8 and RMS is within the range of 0.15 eV. Similarly, we predicted the formation energies of quaternary alloys from their constituent binary alloys. And here also you can see that the R value is greater than zero point 0.8 and RMS is within the range of 0.15 eV. Lastly, the real challenge to predict the formation energy of this equiatomic quinary alloy using binary compositions. And here also you can see that the predictions are quite good with R.81 and RMSE 0.13. In the migration energy case, we use 10 data points from each binary composition, whereas the only difference in the formation energy model, we are actually using 100 data points from each binary compositions. But these 100 calculations are very much possible with TFT. Now, lastly, I want to show some of the interesting observation from our calculation results. And in this slide, I'm showing the effect of allowing element concentration on vacancy migration and formation energies. This plot shows the vacancy migration energies in this quinary base alloy. And here I'm showing the three compositions, and in each composition, one element has a higher concentration and other elements have the same composition. So for example, in this green curve, or um, it's a higher concentration of copper. Copper is 60%, and rest of the elements have 10% concentration. And you can see that the green curve is for higher copper concentration, and orange and blue is for the higher concentration of iron and nickel. So this is showing that the higher concentration of nickel and iron increases the migration energies, whereas higher concentration of copper decreases the migration energies. Similarly, for the formation energy case, we observe the same scenario, that iron and nickel increases the formation energies, whereas copper decreases the formation energies. So these results will able to understand how diffusion kinetics happen in these concentrated alloys. So here I want to conclude my presentation. We have developed machine learning framework for the predictions of point defect energies in these concentrated alloys. The machine learning framework is able to predict the energies of ternary, quaternary, and quinary alloys from their constituent binary alloys. And this framework is right now applicable to, or it's from the interatomic potential calculations. But our future goal is to test and develop machine learning framework for the DFT calculations. Lastly, I would like to thank my advisor, Dr. Aidi, for his guidance. And also, I want to acknowledge the support of fellow group members who helped me on this project. Um, Thank you all for your attention. And here I will take if you have any questions. Thank you.